Hello everyone. Um, my name is Satej. I'm here to speak on the topic of integrating graph context using with supplementary OpenSearch interface for enhanced RAG application performance. And before I start, I think I understand everyone should be or would be super excited about the final IPLs today, but hope we have some patience. And okay. And just before I start, just a brief disclaimer that all the views expressed here are completely mine own and not related to any of my employers, my work. And before I start, I just want to, have a quick show of hands about. I think I saw some of the hands raised for the application or understanding of RAG in general. But I would also like to understand how many of you have idea of a graph database. Okay, good. And how about using graph knowledge for any of your queries, let's say in the context of large language models or generative AI? Okay. I see a few hands. So I think that's a very good opportunity for all of us to learn together. As I think we saw from today, some of the sessions like related to RAG in particular, it is fantastic for, I think, grounding LLMs, particularly to reduce or elevate, the hallucination effect. But it's more precise for semantic retrieval, and we'll talk about what the semantic cortex lays out. But one of the downsides is that it's very limited in terms of the personalization effect. And we will see in terms of how adding a graph layer to your RAG application has some of the side effects, benefits, and what are some of its downturns of using it. If you think about graphs in particular, they're more about relationships, how different nodes connect to other nodes, and what are the relationship context which is set between these two nodes. In today's session, we'll see how we can use a vector database like OpenSearch along with a graph store in the context of a RAG application. This is, I think, everyone understands what a classic RAG looks like. You have a user query which is passed through an embedding model, and you generate the embeddings. And then you compare the embeddings to the OpenSearch through the neural search interface. And when you get these matched documents, you pass them to a large language model, which gives you kind of the natural language response in the context of the user query and the documents. So this is what happens, which I talked about. You have the user query which passes through the embedding. You have the KNN search, which searches through the OpenSearch vector index. And you search the top K documents and pass it through the LLM prompt. The result is that it is very good relevance, but the context could be very shallow. I'm not saying it is always shallow, but could be shallow. And the question is, are you ready to use it in your application context? Because based on your application context, let's say if you're in the aerospace or healthcare domain, you don't want to be shallow, you want to be perfect there, right? You want to be near to perfect, if not perfect. So I think the most important part where the graph layer helps is to explain why an answer is correct in terms of the traceability. When you think about a graph, let's say, we'll talk about a very simple analogy here. Let's say a very simple query, and you might see this query throughout your study. Let's say if you have a few documents and you have a very simple query. Who are some of the founders, previous workers in Google, maybe for context, who have set up their own startups right now? When you think about this, you have a few documents, and when you search using a RAG application, what the RAG application will do is it will just do the very first search for you and give you that document. So you might see some names there, and you'll get a relevant answer here. But it will not give you all the founders there, because it was not able to find all the documents, and it was not able to relate to, because the relationship was missing there. So let's talk about some of the limitations of document-based RAG, or simple RAG architecture. So it's very query specific. So when you ask a particular question, like the example I just gave, give me the name of all the previous Google employees who are now startup founders. So that is very, if you try to find the answer on it, you'll get very relevant document specific answers to it, not very contextual like the whole relative answer which we want. The second is, RAG application is as better as your embedding model, because whenever a user queries, the queries are converted to an embedding format, the vector format, and how efficient or good is your vector is all dependent on your embedding model which you used, because the embedding model itself has a vocabulary of its own. But let's say if your industry has a very particular domain knowledge and that is not represented in the embedding model, you might not get the very relevant answer. You might say that I learned RAG somewhere, I have all the components here, but I think I'm doing everything right, but I'm not getting the right results. You might think that it's not searching the right document, but I think the large language model might not have all the context there. So that is the embedding layer, again needs to be fine-tuned then. And fine-tuning has its costs, so let's not go there for right now. The third part is the context length. You might say that, okay, how about, let's say, I'll fetch 10 documents instead of 5 documents using RAG, and I'll fit it all together into the context. But you might not have that much context window. Maybe your users might not wait for the the whole context to fit together, and there's always a latency towards it too. So when you think about it, it's always a trade-off. You want it to be fast enough, you want it to be cost enough, cost benefit analysis should be cost efficient too, using a large language model. And given that you also have agentic AI, another question, how many of you know about agentic AI? Okay, perfect, good. So now if you think about agentic AI, you might have a very complex application which is doing a lot of other things, and you don't want very large models for each of them, because you want them to be fast, connected, and very concerned about the particular domain they're working for. So that is where the context length is a challenge there. The fourth is the disconnected data. So let's say you have 5 documents, they might not be saying that they are founder, but one document might be saying they are the founder and another document might be saying they are the employee. So these 2 documents are separated altogether. You might by chance or luck have some overlap between them, and those documents might come into your RAG context, but that leaves it to chance, right? One of the ideas about, I think, it's a bit, I think, not so recent, but RDF stands for Resource Description, Framework, and what it does is, it lays out a protocol for you to define your actions or events. So let's say person A who works at employer A, right? So if you think about it, it has three parts to it. It has a subject, it has an object, and there's an action or relationship between them. So that is what the resource definition does it here. So if you see this particular example, each object is related to another through a particular relationship here. And if you think about all the conversations or actions which we do on a daily basis, they're all represented in the form of triples here. So two bodies related together through a relationship or an action. And very similarly, you can think of them as triples. They are also called triplets because you have three parts to it. So here you can see that there's always a relationship between two people through a particular abstract identity. Now coming together here, how do we correlate this to a knowledge graph? Now if you think about this particular example, there are a lot of shops here which says where it is located. So there is a shop information, there is a location information, and if you see there is also a country information because it goes to which country, which, so a lot of other information are all connected together here. And if you can think about, these are all triplets or RDF related identities. If you think about the Big Bucks Cafe located in Seattle, it's a triple. So it represents two objects related through the idea of located in. Now if you see these three triples connecting to other triplets, you see a whole knowledge graph functioning here or being created. One of the examples which I wanted to share for this context is, let's say, talk about an travel application where we want to know, as a user, let's say, if you think about any application, let's say Make My Trip or any other like TripAdvisor, all this, if you think about, they have a few properties. You can think about users, destinations, what activity you did. The relationships could be where you visited, not only that, but what are the points you're earning through a loyalty. And so if we think about this particular example, so everyone now has an idea of the RAG architecture. If you see here, if we talk about step 1 and step 2 and 3, leaving out the graph part which you see in the blue section there, that is the classic RAG flow. But what we want to bridge here is we want all the relationships, like what are the related documents for a particular query. So what we can do here is, we can use another large language model to give me because you can store all these relationships. Let's say I want to store for a particular travel application, I have traveled to this particular location on this particular date. Along with me, let's say I have other, let's say, family members too, who are also, users of this particular application. Now with this in particular, there are particular relationships, and these relationships can always be maintained. Like what LinkedIn does is that if you have a network of all this points out, you can always connect them together. So all these connections are present in your graph database, and this could be Neo4j or Amazon Neptune. So what you're asking the large language model is, create a query for you which gets you all that particular data or relevant relationships. So now what the large language model does is it creates a cipher query which is relevant to your graph database and fetches all the relevant data. So now what you do is, you have the graph context there, which is the graph related data, and the large language model formats it so that it can again be fed into OpenSearch, because that is now your contextual data, and you find more relevant data specific to those embedded data sets. And with open source, finally, when you search all the relevant data, you feed it to the final large language model, which gives you the response back. There are two aspects here. First is that instead of one large language model, you're using two large language models. So your latency increases with the increase that you have a better context or the relationship with more concreteness. The third part is that if you see here, this now brings about what is the difference which you can see when you're simply using vector search versus the graph traversal. With vector, you get a very dense semantics of knowledge, while with graph, you are getting the explicit relationships. And when you combine both of them, you're getting the personalized multi-hop. And one concept here is the multi-hop idea, because if you see here, you're hopping through different documents here in particular. First is getting the knowledge from the graph database for all your contextual knowledge. And with that particular information now being fed, you're again searching for all those relevant information in your OpenSearch vector store. With the vector search, you may be using a flat ANN architecture, while a graph, it is very cheap joins, which, because graph has a better idea of where the relationships exist. And one of the prompting layers is you have to share the schema of your graph relationship so that the large language model knows which data exists in which format so that it can create a query based on the user request. So this is one of the example data sets which is present in the graph database, with an example like the user data, for example, based on ID, which destination they travel to, with an activity, and what are the interactions. So let's say they're reviewing points or searches. And all of this, if you think, can be represented in the form of a triplet, because all of them could be nodes and relationships. If you see this particular aspect right now, we are trying to bring about a different architecture here. Because one of the disadvantages with the previous one was that you were looping or iterating towards two large language models, although that was giving you more concrete groundedness than the simple RAG model. But we want to make it more faster. So here what we are trying to do is we are trying to use OpenSearch as a graph layer. So we are trying to remove the graph database and implement the semantics of how graph layers are built by using triplets into OpenSearch. So what here happens is, whenever, and we all understand that there are two layers in terms of how your embeddings are created. First is a background process, because we have a lot of documents specific to your organization, which you want to convert to embeddings. So that happens in a background process in some pipeline somewhere through a ETL channel. The second is more on a real time, when a user questions something. So you're converting it to an embedding. Now the NER pipeline is what creates a named entity recognition. So whenever you question something like, person A has traveled to location A. So there are three entities here. There's a travel entity, there's a person, and there's a location entity. So you can use any tool like named entity recognition, which creates these three parts for you. And this has to pass through this pipeline here. Now from this, you are getting this triplets idea from relation to. And this data can be stored in your OpenSearch in terms of metadata, embeddings. So you might have previously only just one field for your content, but now you're having three fields, to represent these three data sets here. Now what happens, previously in your simple RAG case, you were searching just for a single field for the data. Now instead what happens is whenever a user queries something, you convert it into the triplets form, so that now the query which you are forming to your OpenSearch database has a from part, a to part, so that it matches based on these two new metadata forms. So that is what happens at the very right. If you see, you have the matched documents which have now come up, and you might not always get the from and to parts. You can always make a judicial decision whether you take the from or you take the to, so that you get a combination of data there. Once you get the documents, the second challenge comes is, because you have used a NER pipeline here, so you have kind of dissected the information of the user query to three parts here, and also your documents. So the responsibility lies with you to combine them again, because that is what your large language model needs eventually. So you'll need a concat and a formatting layer in terms of adding and combining them back together. And I think it should not be in the very right kind of the format of language in a correct grammatical format, because I think large language models can understand that it's a triplet, they understand the relationship, and they can build the idea or the knowledge for you there. Coming to the NER pipeline, this is what it could look like. And here I'm just sharing an example here. Let's say you're using a travel application, you're booking something, you're traveling somewhere, you booked a flight, you liked a particular review someone left. So all these are particular events which are happening. And if this event, you could be catching them in some logging interface. It could be a CloudWatch, or it could be a queue. You just need to feed it towards a Lambda or a serverless layer and generate through Amazon Comprehend or something, and feed it to your triplets. So you're generating triplets out of it and storing it. So all this happens in an asynchronous manner, so that you not only have your documents, but you also have your activities which are being fed into the triplet layer, into OpenSearch. So this is eventually what happens altogether. Now, these are some of the effects of the changes which we are talking about. So, if you talk about the recall, previously it was kind of 0.71 if you compare, only by using the vector database, but with the graph it is a bit better, like 0.86. With the delta, so it results in a delta increase of 21%, which is good. And the mean response time is 0.53. And with the graph it increases to 0.64, which is plus 11% increase. The third part is the number of tokens used per prompt. The first one, on an average, that was 3,200 for the example, while with the graph it has reduced by 2,400 if you're just using the graph layer, but if you're using a combination it might increase with the third. And if you see, there is a latency increase of a few milliseconds, because you're passing through not only the query layer of the graph, but also the another large language model. There's a very sample query if you can correlate with it, and it just says, where should I redeem my 5,000 points this summer with my kids, right? So there are a lot of, if you think about this, it has three parts to it. It relates me to the idea of redeeming, and the third part is the 5,000, right? The 5,000 points. So if you think about this, if I feed it to a very simple RAG model, it might not give me all the information, because, and I'll come to the agentic part too, because if you see here, there is some dynamism here. Because when you say my 5,000 points, it has to go back to your database, fetch some information to, because this dynamic information might not be there in your static contextual data. Now, what it can eventually do here is it will give you a personalized shortlist like the places to visit, because it's saying that there is a summer part to it. So it needs to fetch all the places where summer could be correlated. So that is where the graph layer helps you. It brings those particular aspects of the locations. And when you say with your kids, right, and it should not be very as simple as that, because again you can think about this query being converted into two triplets. It cannot be as simple as a single triplet. It can be 2 or 3 triplets, which you can again pass in query. So coming to here, I wanted to understand if there is any question in particular relevant to this part here. Okay, perfect. So some of the lessons which are learnt from this example or the use case is that when you think about the challenge of it is the named entity recognition part, because you have to always validate whether the information the user is querying is rightly converted to the form which could be used for your application. If your named entity NER pipeline is giving you different constructs altogether, which is not matching with a user query, then your whole pipeline or the architecture is not working to give you the expected result. And so that is a very important part to always check about the NER pipeline. The second part is when we saw how to combine that data back. So I think that is also very relevant, because if you think about the graph also, it can give you a lot of information together. So you have to filter at each layer by providing some limits so that you don't exceed at each triplet layer as to what you're fetching back. The third part is very important, I think, to use a caching layer, because I think that's always or many a times forgotten. Because if you see a lot of queries which are very relevant to you and which have very common groundedness, you don't need to pass it through the whole RAG layer. You can just fetch the contextual information, give it directly to your RAG LLM model so that it can give you the answer back. Or you can even bypass the LLM because you always have an answer together. So you have to determine where you're feeding that particular response or the caching layer at. The most important part, I think, not only here but building any RAG application is to check for accuracy, because I think we see a lot of content altogether in the cloud and everywhere that this works, but it works for different contexts and different applications. So you have to see whether it works for you, because eventually you have customers, and when you're bringing a new tool together, you have to test it out, whether it's giving you with the same latency, with the same response. So I think feedback is very important. Even if you might be 80 to 90% sure that it's working, still get feedback from your customers, whether it's improving the experience, whether whatever answers they're getting is relevant to what they're saying, so that you can feed it to your fine-tuning layer, or you can give it back to your developers who are developing this. The second is to build observability into it, because maybe you build this whole pipeline together. It gave you some latency when you're building it, like let's say, as I did show 890 milliseconds somewhere, but you never know what happens in the real world. It could be stuck somewhere 1 minute. So it's always good to build those observability. So on the real time, where the issues are happening, and you can give a solution to it to your customers. The last part is, I think it's talked a lot right now. A lot of cloud and other vendors are building agentic interfaces. I think that's the some of the traces of where it is going. So I think RAG as part of the graph plus RAG built on an agentic layer, because maybe the very first time you're trying, may not give you the response, but you might need some tooling layer to fetch some database or some answers together, or get some more information from the customer, right? Because you're not getting. So those are some of the decisioning layers which needs to happen in your agentic layer. And whenever you are building this agentic layer, you have to be careful enough that you're not reiterating too many times, because you might be thinking, okay, it's too intelligent, let it take the decision, but maybe it's always making some decision, right? Okay, so I think that was all about, there's a very short introduction about me, and these are some of the books I've written. One of the others, I think, which will come in the summer is relevant to generative AI, but is more relevant to Java, because I think that's a very specific environment, very specific to Java developers. And there's a very short code if you're interested in any of these to buy. Yeah, thank you.
Thanks, Satej, for giving this insight. It's pretty interesting and insightful. Hope you guys have learned much. The floor is open to questions. I'll start with one. I know that he started it, but didn't get a chance.
Hey, yeah. Okay, thank you so much for taking this concept. Actually, we are dealing with this issue. Everything you mentioned is we are facing this problem. First question is regarding the graph context. Are you saying that like we can save triplets in OpenSearch?
Yeah.
Is there any example basically how do you save a triplet in OpenSearch and how do you retrieve?
So I think there's a GitHub example in the slide. You can just check it. So the examples are there highlighted.
Okay.
That should be.
Sure.
Yeah.
So this is everything like graph context inside the OpenSearch only, right? Not using Neo4j or Neptune or something.
So I think there are two examples, right?
Yeah.
The very first part is you can use a graph layer on top of it.
Okay.
As I did show in the very first. So use a graph first. You fetch all the relationship, and then you feed it as a further query to your OpenSearch. So there's two layers to it. So there was a separate graph layer.
Correct.
Now, when you talk about OpenSearch in separate, so that's where you are representing these as metadata layers, the from and to. So you're searching, not only based on the embedding, but also, based on your metadata too. So on the from and to. So you're getting more context there.
Okay. And suppose say you have n documents. If we introduce triplets, will the final number of documents will be n, or will it be replicated? I'm just asking whether there will be a data duplication or what.
When you think about the data duplication, there is a side effect of it, because again you have to think about what you're querying. It all depends on how formatted data you have already stored in OpenSearch, because that is the very important layer. You're already storing duplicate data in OpenSearch, because I think one of the layers which could be missed in the architecture is that when you saw the NER pipeline, whenever an activity is happening, you're converting it to a triples and you're storing it in OpenSearch, right? In the 3 data metadata format. But we are not checking if it is already present. So I think that is another layer which you can check. And I think duplicacy can be elevated at 2 levels. First is at your pipeline level where you're storing. So you check previous to storing, whether it's already present. The second is, even if there is duplicates, I think the large language model will help you there. But I think the context size increases. So I think that is the challenge there.
Yes. Okay. Last question is basically, does it support multiple index for triples?
Yes.
It does.
Yes.
Okay. Thank you so much.
Thank you. Anyone else?
Thanks for the great insight. I just want to ask, the approach you mentioned, the second approach where we are storing triplets in the OpenSearch, is that an idea or that solution already working well in the production environment?
Can you repeat the last one?
The second approach where we are storing all the relationships in the OpenSearch, right? That solution is in the production or just an idea as of now?
So it's in a use case. It's not a production use case, but there is a prototype which can be checked in the link.
Okay, thank you.
Any other questions? Yeah.
Okay, my question is regarding the embeddings basically. Suppose say the content is too huge, and usually Titan gets like around 1,000 characters or something for embedding it. What do you do when there is large articles where you need to embed it? How do you deal with the embeddings basically?
So you're talking about the retrieval part in the RAG layer, right?
No. The embedding layer basically. The input to the embedding layer, the content is too huge. So if you chunk it, you lose the context.
Yeah.
Yeah. So without chunking, is there any way, or how is that?
I think it has to be a combination of both when you think about it. And it all depends on your data at first and your use case. So let's say if you are storing very big context in your, the triplets layer, I think that affects you because you're eventually querying a lot of data here. There are a few checks you can use. First is you can do a similarity on other metadata which you can store based on some tagging layer, to further filter it out. Second is, previous to that, if it still doesn't help you, you can go back to the graph layer which was there, because maybe it increases a bit more latency for you, but I think it stores the graphs, and I think some of these also provide those embeddings with it. So when you have the relationships, they're also giving you based on the embeddings query, which I think Neo4j supports. So I think you are fetching already one embedding layer, filtering it out, and providing it to the the OpenSearch, which contains a bigger context data for your whole document. So you're kind of separating it into 2-3 layers out here.
Any further questions?
So when we store the triplets, that is from, to, and the relation in OpenSearch, can we store it like as embeddings as 3 things, or is it better to have one field which has like, we format the data and put it as from to, from relation to, or have it 3 different fields and have those embeddings there?
It again depends on it's a nice thinking when you think about how you can use it. When you use a whole triplet in a single field, you're getting more, I think, on a single data, it also gets that context. The limitation of it is that you're putting all of this in a single field. And if you think about it, your query could be a bit adaptive, because it all depends on your NER pipeline as to how you have formatted this. When you put it into 3 layers, it gives you more flexibility, I think, because you can query it in different ways. Let's say if I just want to know from which location I'm traveling from, right? So I don't need the other information, and maybe that could give you some confusing results on that. So if you separate it out, you have some flexibility in terms of how you query it. So it's just a trade-off. You have to experiment and see what works best for you.
We'll take this final question.
Yeah, so I wanted to ask, like, how accurate has NER been in tokenization or getting those triplets out? And like in my experience, NER, I have struggled with getting them to be accurate in my use cases, right? So do you have like a fallback mechanism to deal with those kind of edge cases? Like, how do you approach that?
So I think two aspects. First is when you use a NER, it again depends on how accurate your training is, because again NER is a model based. It depends on your vocabulary, so it has its challenges. The second part is it's always good enough if you have your context. So let's say if you want to limit your application to a very specific domain, which you already have a context around, you can build a very fine-tuned, NER model on it. But let's say if you don't have the expertise in your in the team or the skill set for that. The second is, even if it might not give you that, you can always choose, kind of combine it with the simple RAG to, get more contextual information. Because if large language model gets all this two information, it can still help you. Even if the NER is not performing, your proficient large language model could fill in that gap, I would say. If I may think also, if you think about NERs, I think a large language model could also fit in there. It's sometimes, when you think about this concept of when you convert anything related to natural language, a large language model ultimately fills in because it's now very generic enough to fulfill all these functionalities. So I think there also it could fill in because it has a very large context, but it adds another latency to it.
Thanks, Satej. Folks, feel free to connect with him after this. He'll be around here, and also he has some few sessions tomorrow, I guess. So you can connect with him tomorrow as well. We can take a 10 minutes break. The next session is about scaling in petabytes for log management. Might be interesting for folks to be here and hear out through. So we'll start in 4:35. Yeah.
Thank you so much.